Hello, everyone. Uh, so I hope everyone is back. And so, do you have any question regarding what we have discussed so far? Okay. So, let's see. Let's get started then. I hope everyone is back. And yeah. So now we are going to look at trusted computing. And here I've just opened web and I am going to uh, say read first paragraph here from Wikipedia. What does it say is trusted computing? So it says that trusted computing TC is a technology developed and promoted by the Trusted Computing Group. And what is this Trusted Computing Group? So this Trusted Computing Group is a consortium of these different companies, like these different enterprises: AMD, HP, IBM, Intel, Microsoft, and Cisco. Okay, so this is a group which was formed in 2003, and then this group has developed the technology trusted computing. Now, with trusted computing, the computer will consistently behave in expected ways, and those behaviors will be enforced by the computer hardware and the software. And enforcing this behavior is achieved by loading the hardware with a unique encryption key that is inaccessible to the rest of the system or the owner. So with trusted computing, we're relying on our hardware, and we're saying that the hardware has a unique encryption key which is inaccessible to the rest of the system, even the owner of the system. So this encryption key or this trusted hardware is manufactured. When this hardware is manufactured, the manufacturer is going to uh, put a key inside this burn a key inside the hardware. That key is even inaccessible to the owner of the hardware. So even if you buy that hardware, you cannot have access to to that encryption key. And now and then, using this hardware, trusted hardware, as the base, as the base of uh, basically as the base that the basis is that it is the basis is the privacy of this encryption key. We are going to build some mechanism which are going to guarantee that the computer consistently behaves in the expected manner, and that is called trusted computing. Okay. And apart from that, and we are also going to look at one such hardware, which is the TPM, Trusted Platform Module. So a TPM, or a Trusted Platform Module, is a physical or embedded security technology that resides on a computer's motherboard or its processor. And TPM uses cryptography to securely store essential and critical information on the PC to enable platform authentication. So what it's saying that TPM is also a piece of hardware, and it uses cryptography, and then it is going you can leverage it to store some critical information inside your hardware, and you can use it to perform authentication. Now we are going to look at TPM, and we are going to start with trusted computing. And here I'm using notes from Professor Vinod Ganpati. So these are handwritten notes by him. And in this, we are going to look at trusted computing and attestation protocols. So now what is the problem that we are trying to solve here? The problem is that how does one attest the software stack running on a remote machine? So the problem is that we want to build trust into a machine. Okay, so we just said that trusted computing allow us to ensure that your machine is always going to behave in an expected manner. Here, the expected manner, what we are trying to verify is that your remote machine is is running a particular software stack. Now, what does attest word mean? So it might be a new word to some of you. The word attest simply means to verify the truth value. To simplify, verify that some value is true or not. Okay, some so it's that is what the word attest means. Means the verification of something being true. Okay, and remote machine. What do I mean by remote machine? So let's say I am running some application on a cloud, or I am running some application on a device which is not directly accessible to me, and it is located somewhere else. So that's a remote machine. Okay, and now as a user of that machine, as a client of that machine, I may be interested in knowing that what is the software stack running on that system, like what is the operating system, which operating system is running, which other applications are running on that system, and so on. Now why is that important? Now that is important because let's say I am the client and I want to ensure that, like, maybe I'm running a very sensitive application. I'm doing some sensitive computation on this remote machine. And I do not want any other application which is not trusted, which I do not trust, or any malware application to be running on the same machine. Because then the malware application can try to learn the computation that I'm doing. It can try to steal my data. So that's why I want to know exactly what is running on that machine. And so the problem here, what we are looking at is how can I know what is running on that machine, and how can I trust that that software stack is the only thing which is running on that machine. So let's say this remote machine can be your, let's say, a cloud, right? So, and let's say I am a client and I ask the cloud provider, okay, okay, please tell me that what is actually running on this remote machine where my computation is being run. Now the cloud provider can tell me, okay, I am running this Windows 10 and this is the version, then I am running this Apache server and MySQL server, and these are the versions and so on. And it can say this is the software stack I am running. Now, as an end user, can I trust the cloud provider when the cloud provider says that this is what it is running? So the cloud provider is also it's like a third party. I cannot trust that what the cloud provider is saying. So then I have to have a mechanism, like I need to ask this cloud provider to prove to me that, provide me a proof by which I can verify that you are actually running what you are saying. So if you're saying that I'm running a Windows 10 OS with these applications and these versions, then I want to be able to verify that this is actually the software stack that you are running. Okay, so the attestation protocols, so these protocols verify that something is true. Okay, so these attestation protocols are actually basically you can think of it like a message exchanged between these two parties. One is, say, you, who is the cloud uh, user, so you are the client, and then the remote machine which is run by the cloud, which is a third party here. And the attestation protocol is basically the messages exchanged between these two parties. So you are going to say that what is the software stack running on this machine? Then the cloud provider is going to tell you that this is the software stack, and then you're going to ask that, okay, prove that this is the software stack which is running on the machine. Now, and Now, the attestation protocols is basically a way in which allows the this cloud provider to prove the integrity of this software stack which is running on this machine. Okay, so it's a mechanism which we are going to look at now with the, and it is enforced with the help of the trusted hardware. And this mechanism allows the cloud provider to prove prove that it is actually running this particular software stack. So in an attestation protocol, there are these two parties. One is the prover. So here the cloud provider is the prover and you the verifier. So cloud provider needs to prove the integrity of something. Here it is the software stack, and you the verifier is going to take the proof which is generated by the cloud provider, and then you are going to take that proof, verify that whether it holds true or not. So to repeat, so in trusted computing, basically we want to verify that something is true or not. So the computer is actually behaving in the expected ways, and we do that with the help of a trusted hardware. Okay, that's what we said initially. Then we are in conjunction with trusted computing, like we are going to look at this attestation protocol. And what is the attestation? Attestation is just a technique, okay, which allows one party to prove the integrity of something. So in this case, the software stack, to the other party. So there are these two parties, one is the prover, one is the verifier, and then they are going to engage into this attestation protocol, which is a set of, which is like a challenge response protocol, where the client is going to send a request to the server, to this cloud provider, asking to prove the integrity of the software stack which is running on the machine. And the cloud provider must send the software stack it is running, along with like the details of the software stack it is running, along with a proof. And this proof will be verified by the by you if you are the cloud provider user. Now this will become a bit clear soon, that what is this proof, how we generate such a proof. So I hope that the problem setting is clear. And if it is not, then please let me know. Is there any question about the problem setting? Okay. So what do you, so this we have already discussed. Uh, okay. Can you tell me what is attestation? What did you understand from this, that what is attestation? Yes. So it's a way by which the service provider here can prove the integrity of, say, the software stack or the computation which is happening here. So it's a technique, okay, and which allows one party here, the service provider can also be called a prover. It allows a prover to prove the integrity of some property. Here the property is the software stack, to prove the integrity of something to the client, to some other party, which is the verifier. Okay, so this is one, this is the problem. The problem here is to attest something which is running on the remote device. And That's the problem setting we talked about. Although, one second. So let's now look at these applications of attestation. I hope that this is visible to everybody. Yeah, so let's now look at the applications of attestation. So, the first application that we have just discussed on the last page is in cloud computing, cloud clients may wish to ensure that the cloud provider is indeed executing the software stack promised as part of the service level agreement. So your cloud provider has, say, promised or has say advertised that it is running this particular software stack, and so as a client you may wish to ensure that the cloud provider is actually running this software stack. And there are, as I said, there can be different reasons. Of course, for this one is security. You want to ensure that there is no malicious application running on this device and on this machine, and the machine is always started in this uh, with this software stack which you trust. Okay, then the another application is remote billing. So suppose the server charges the client based on the resources consumed by the client code running on the server. So if the client code takes, say, some particular amount of memory and some particular amount of CPU cycles, then based on how much resources are consumed by the client, the cloud provider charges the client. Okay, and then the server produces a bill at the end. So it will produce a bill. Now, how does the client trust this bill is correct? Because the server is producing the bill at the end of the day, and you as a client, you do not know how much memory, let's say, your program is taking, your computation is taking, or how much compute cycle your program is taking, right? You may not know. uh, so then how do you trust that the bill that you're given at the end of the day by the server, it's actually a correct bill? So one of the solutions with cloud with this attestation is this, that the client and the server together can agree on a billing software that the server will be using. So let's say the client and server, they both are going to agree on this billing software. And what does this billing software contain? The billing software contains, let's say, the rates for different things. Like, say, if you use 100 GB of, if you say you use 1 GB of memory, then this will be the cost. If you use this much memory, if you go beyond 100 GB, then this will be the cost, and so on, and for compute, etc. So let's say this is a software where which consists of all of this information, which is like these rates that are applicable, and this is the software which has been agreed upon between the client and the server, that this software actually contains the rate which were, say, advertised by the server. Now, if the bill is actually produced by this billing software, then the client can trust that bill. That, okay, if the bill is produced by the billing software, since the client knows that the billing software is correct, then it will trust the output of the billing software. Now, the client only needs to establish that the correct billing software is running on the server, that the billing software which is running on the server is the correct billing software. So then client can ask the server to attest its software stack and then ensure that the billing software is running. Okay, so the problem is remote billing. So if your service provider is saying that, hey, this is your bill and you have to pay, and you have used X amount of memory, Y amount of compute, then how do you trust that that is actually what you have consumed and that is the amount you should be paying? So the solution with attestation is that, let's say, you agree with your cloud provider on a billing software which you have, say, looked at, and you have verified that this billing software is has correctly, say, coded the rates for either compute and memory, etc., for the resources. And then at the time when the cloud provider is running your computation, or when this cloud provider setting up the software stack for you, then you can ask the cloud provider to provide a attestation of its software stack. And then you can look at that software stack, and then you can ensure that the correct billing software is actually running. So then you can trust the bill if it is produced by this billing software. Of course, the next application is malware detection, which we also just said, that malware detection or proving the absence of a malware. So client may wish to ensure that the server is only running a good software stack, and the client can refuse to give its business to the server otherwise. So the client can first ask to prove the integrity of its software to the service provider. I mean, if it fails to do so, then the client will not run its computation. So, and the last one here, although this is not the end of the applications of attestation, there are many more. The one we have is corporate settings or enterprise mobile devices. So, uh, so there is this trend which is called BYOD, bring your own device, which allows where the enterprises allow the employees to use their own devices uh, for doing the work. Like for work purpose, if your enterprise is, let's say, allowing the employees to use their own device, etc., then the company is, let's say, going to give you a virtual machine setup that you can use on your own machine, on your own laptop, and then you can do the work on your own laptop. But then the question is that how does the enterprise ensure that the employee's device is free of any software that can potentially steal the company's corporate assets, such as the code and the internal documents, which is being run on this machine? Okay. And so this is can also be ensured with the help of attestation, because then the enterprise can ask the employee device to generate a proof of its software stack, and then ask it to verify that to ensure that the software stack is free of any malicious software. So are the applications clear with for attestation? Okay, so now for all of this to be possible, for all of this, to implement attestation, the client needs to have some root of trust on the server's device. Okay, now how do you trust? So you are saying, okay, to the server that, okay, provide me a proof. Okay, now how will the server generate such a proof? So to generate such a proof, the server needs uh, like something that you can trust, that your client can trust. So I'll say, okay, I can trust the hardware, the trusted hardware which is there on your machine. Say I can trust that hardware. And if the hardware attest, if the hardware generates a report of the software stack running on your device, then I can use that to verify that actually that is the software stack running on their device. So as the verifier, so the verifier, which is here the clients needs to have some root of trust on the server side, and the server must use that root of trust to generate the proof. Okay, so what can be this root of trust? So the basically the entity, what is the root of trust? I mean, basically the entity that you can trust. The entity can be anything. It can be the hardware, it can be the privileged software such as OS. But here, what are you asking for verification? You are asking to verify the entire software stack on the machine. So that's why you do not trust any software. And therefore, You're saying, okay, I do not trust any software, I only trust the hardware. So here the root of trust is the hardware, the trusted hardware. Root of trust can be any entity, actually. It doesn't have to be a hardware, it can be any entity on your machine. It can even be the software, such as which is running in the privileged mode, such as OS. But for the current problem that we are looking at, which is the attesting the entire software stack on this machine, we do not trust any software basically. So we need to go down in the computer layers, and below the software stack is the hardware. And you're saying, okay, as a verifier, as a client, I only trust the hardware that you're using, and uh, I want you to attest to me using this hardware that what software stack are you using. Okay, so that's the root of trust on the prover side, which the client is using, which the client is trusting or needs to have some trust in. Is that clear? So what when so the trusted hardware comes in actually many forms nowadays, and the earliest form of trusted hardware is TPM, trusted platform modules. And this is the first widely deployed commercial trusted hardware mechanism, which is very widely deployed, and it is likely to be present even on your laptop. So, and it is accessible using a device driver. So, and this is what we are going to look in, I mean, in these notes. And after that, we are going to look at ARM trust. So, other popular trusted hardwares which have become popular in the last decade, they are like, I think ARM trust zone probably dates back to SGX, although I'm not sure, but I think so. So the other two popular trusted hardwares are SGX and ARM Trust Zone. SGX is from Intel. It stands for Software Guard Extensions. And ARM Trust Zone is, of course, from ARM. And so how are so the both of them are also trusted hardwares. Now, SGX allows you to do a encrypted execution. Okay, so basically it allows, so the computation happens inside a protected memory region that's called the enclaves, and it works on the encrypted memory. And so there's like piece of your there's part of your RAM which is always in the encrypted form and can only be decrypted inside the enclave, and so it allows encrypted executions on the cloud. And attestation is also an important part of SGX. Today, we are not looking at SGX. We are looking at ARM Trust Zone. So ARM Trust Zone is, so SGX is more widely deployed on like server class computers, such as in clouds, while ARM Trust Zone is also a trusted hardware, and it is more popular in the mobile devices and embedded devices. So it's so like in in the mobile devices, so Samsung has used ARM Trust Zone to implement, say, to implement some security mechanisms, and so that particular mechanism which ensures the integrity even of your kernel, the OS, so that is called Samsung Knox, which they have implemented. And they were able to deploy it, like they have a paper. So if you search for Samsung Knox, you will be able to find their paper. So they had implemented it, and they had deployed it into their mobile phones. And it can, we will see today that how an ARM Trust Zone, which is very likely to be present on many Samsung devices, can protect the integrity of the payment apps. So, so to summarize, we to trust to so on the so on remote machine, like here the cloud provider or the service provider, the as a verifier you need some root of trust on the server side. Okay, Now, the root of trust can be a trusted hardware. And trusted hardware nowadays are present in these different forms. First is the TPM, Trusted Platform Module, which is oldest form of trusted hardware, and it's very widely deployed. Although it is like it has less, it has in terms of capabilities, it has less features compared to SGX and ARM trust zone. And we will look at a simplified in a simplified manner. We will look what the TPM can do in these notes. And SGX and ARM trust zone are other trusted hardwares from Intel and ARM respectively. And SGX allows you to do encrypted execution on the cloud. So if you give it some code to execute, that code will be executed in an encrypted form itself, and then so basically anybody cannot steal your data. Well, ARM Trust Zone, it is more widely popular not in the cloud setting, but in the mobile or devices or the embedded device setting. It's actually very widely used in the embedded world, and it's very likely like ARM Trust Zone is uh, actually available on a lot of devices. So and it has been used by Samsung in their mobile devices to protect the mobile payment apps. And we will look at ARM Trust Zone and like how does ARM Trust Zone protect the integrity of, say, the mobile payment app. Is there any question? Okay, if there is no question, let me ask a question then. Mm. Okay, so what is the root of trust? Attestation of the hardware. Not actually. So root of trust, what we are saying is that coming back to this first picture here, okay, the problem is setting is that you are asking, you are a client, I am a client of the cloud provider, and I'm asking the I am asking the cloud provider to provide me the software stack information of the remote machine. Okay. And since I'm saying, okay, then the cloud provider is going to tell me that I'm running Windows 10 and Apache version 2.5, etc. This is the software stack I'm running. Now I want to verify that the cloud provider is actually running these softwares. Okay. So then I ask the cloud provider to generate a proof for this. But for the cloud provider to be able to generate a proof, like I need to have a basis on this. There has to be some basis on this machine that I trust. I'm the client. I need to trust something on this machine, right? I need to trust something. I do not trust the cloud provider. I do not trust the software stack which is running here. So who is going to then provide me with this proof? I do not trust the cloud provider, I do not trust the software stack, then who is actually going to generate the proof? So the entity which is actually going to form the basis of this attestation protocol here, or the firm for going to form the basis of trust in this machine, in this case, that is the hardware. So I'm saying, okay, I trust the hardware. So if the hardware generates a proof of the software stack, and if I know that this proof is generated by the hardware, if I can verify that the proof is actually generated by the hardware, then, and if that uh, proof which is generated by the hardware actually, if I verify it and if I find that it is true that you are actually running this software stack, then then it is okay. So here the root of trust is the hardware. The root of trust is the hardware. It is the entity on the remote machine that the verifier trusts. The entity on the remote machine that the verifier trusts. So if the verifier trusts the hardware, then the verifier wants the hardware to generate a proof. So the verifier wants the hardware generated proof. The hardware is going to generate a proof of the software stack, and that will be then sent back by the hardware, not exactly by the hardware, but you will be able to verify that the proof was generated by the hardware, and then you will look at the proof and then you will verify whether it is corresponding to this software stack which is advertised by the cloud provider. Does that make it clear, like what is a root of trust here, and can be what components can be root of trust? I made a mistake. Software stack. Uh, I am not very sure if you can you clarify further. What do you mean by software stack? Okay, it can be a root of trust. And can you tell me what is a root of trust in this setting? Is for this particular setting? What is the root of trust? Yes. So here the root of trust is the hardware. And why is the root of trust hardware here? Why are you not trusting some software? Can you tell me? Because it gives the integrity of the software stack. Yeah, but why are you not trusting software, say OS? Why are you not trusting OS? Okay, so here we do not trust OS. Okay, we do not trust the OS. We do not basically trust any software which is running on this machine, starting from the OS. So we do not trust any software which is running on this machine, and we trust only the hardware in this particular example. Although the root of trust can be uh, can be, say, it depends on what you trust. Okay, it depends on you. You can say, okay, I trust the hardware, or I can trust the OS, or something else. But in this case here, we trust only the hardware. Why? Because we want to attest the integrity of the even the OS. Because we want to attest the integrity. Attest means verify. Okay, the integrity of even the OS. So we do not trust the OS because we don't even know whether the cloud provider is running the correct OS or not. So that's why we don't trust the OS, we only trust the hardware. And that also because we have this, say we just trust only the hardware, we know that the hardware cannot be tampered with. Okay, so I hope that clarifies the problem and also what we are doing. Okay, right now. Now, can you tell me the which are what are the examples of trusted hardware? So some of these words can be actually new to you, so that is okay. But what are the examples of trusted hardware? So if it's possible, maybe you're hearing them for the first time, and so I have the slides open as well, but I only want you to tell me that what are the different examples of trusted hardware. Yes, so the different type of trusted hardware are TPM, Trusted Platform Modules, Intel SGX, Intel Software Guard Extensions, and ARM Trust. And we are now going to look at TPM, Trusted Platform Module, which is very widely deployed, commercially trusted hardware mechanism. Okay. So the TPM was proposed in the early 2000s, and so we saw that the consortium of these enterprises, that is the TCG, Trusted Computing Group, was formed in 2003. So it was, and they actually developed the trusted computing area. And the TPM, the trusted hardware, was proposed in the early 2000s. And now it is widely deployed on modern chipsets, and it costs very less. It's cost roughly $5 or so. So it's very cheap, and that's why it's widely deployed. And it provides a root of trust on the machine and serves so it provides a root of trust on the machine, and it will serve as the basis of the attestation protocol. And we are not looking at the full specification of TPM, that is definitely very complex, but we are going to abstract away the details, and we are going to look at like only some key ideas related to trusted platform modules. And we have these 6 bullet points here. Okay, these 6 stars, in which we, and in this only these 6 bullet points, uh, we are going to try to discuss that what is a TPM. So the TPM is a trusted hardware which was proposed in early 2000s. It provides a root of trust on the machine, and it will serve as the basis of the attestation protocol that we will look at. Okay. Now, what is a TPM? It's a temper resistant hardware. Okay. So it's a hardware which is temper resistant. Means that if you try to even do a physical attack on this hardware, for example, if you try to put some memory probes or some probes on this hardware so as to learn what this hardware is doing, then you will not be able to do so. Because if you open the chip packaging to read the content of this of the content of this hardware at runtime, then it will self-destruct. So it destructs if you open the chip and try to read the execution which is happening on this hardware. So it provides even the temper resistant guarantee. Like even of the most so physical attacks are actually the most invasive attacks. So you're trying to learn something directly from the hardware, and so even if you have access to the hardware, uh, if you are still the trusted hardware is still going to provide the guarantee that the attacker cannot learn the content of the computation which is happening on the hardware, because the hardware is tamper resistant. The next thing is that this hardware has a public and the private key pair. Okay, so this hardware has been manufactured in such a way that the manufacturer has hardwired a private key uh, in this hardware. Okay, so the manufacturer has put a private key hardwired it in the hardware. And then there is a public key also corresponding to this private key. And the public key is given to you when you purchase the hardware. So the public key is given to the owner of the hardware. And then this public key and private key pair is actually certified by the manufacturer, such as Intel or AMD. And this public private key is certified by the manufacturer's certificate authority. And this private key is hardware inside the hardware by the manufacturer. So if you so this would so to understand this, you would need like if you have learned a little bit of cryptography, then you would know that there are these uh, in cryptography you have the keys here. The like in basically public key cryptography, you have these two keys, private key and the public key, and you use these key and you pass these key to the cryptography algorithm along with your data, and then the algorithm is going to encrypt the data with the private key. Okay, and then data is called the ciphertext. So it's we are so here, if you do not know about the details of the cryptography, then don't worry about this, just understand that these are the encryption keys. Okay, so these are the encryption decryption these are the encryption decryption keys. So this is the private key and this is the public key. Then after that, there there is the third thing. The third thing is that your TPM is capable of performing the crypto operations. Your TPM is capable of doing encryption, decryption operations like simple RSA encryption. Okay, like it can do simple encryption, it can generate digital signatures, so it can generate a signature over some value which can be then used for authentication. Okay, so digital signature, you can just think of like that it's just a signature similar to like we signed. So it's a but it's a digital signature which is generated using this public private key pair. And so basically the private using the private key, and when you provide this digital signature to some party, then that party will be able to authenticate that this digital signature was actually generated, that this digital signature is actually from the hardware. Okay, then after that, the hardware stores the data securely in the on-chip registers. So the hardware is has some registers which are called platform registers. configuration registers or PCR, and the hardware is going to store the values, secret values or confidential values into these registers, and they are never stored into the memory. Okay, and so there are about 10 program platform configuration registers, and they are used to store data securely in on-chip registers. This is a onboard secure storage, and it may also have a onboard secure storage, which is not accessible by any other software. Okay, so it is only accessible by the hardware. Now, what does it? So these are the capabilities of this hardware. Like first is it is temper resistant. Second, it has a private public key pair where private key is hardwired in this hardware by the manufacturer, and then it is able to perform crypto operations and like encryption, digital signature, and it can store the data, and it has these on chip registers, uh, which are also of course temper resistant because they are part of this hardware, right? So it has these on chip registers and also a secure storage on the board, which where it can store some data securely. And there are about 10 such registers. The registers are called platform configuration registers. Now, how can we use the hardware? So to use the hardware provides supports an API. It is called the TPM Extend API. Okay, and this is an API which is supported by this hardware, and this API can be called by the device driver, which is going to like communicate with the hardware, and then this API extends the content of the PCR register with the supplied value. Now, what does extend mean? We will look at it in some time. Okay. Now, this has a complex key hierarchy, but I am just going to skip this because I think this is already too much detail. Uh, so let me, so then let me reiterate. So we are currently looking at TPM, which is a trusted hardware. Okay. And the TPM, so TPM stands for Trusted Platform Modules. It is a hardware, and this hardware can serve as a root of trust on the machine. And why? Because it's a temper resistant hardware, which so the attacker cannot even mount a physical attack on this hardware. This hardware has a hardwired key. So a private key is already embedded inside this hardware, which is not even available to the owner of this machine. And it is only accessible from within this hardware. Okay, and so this key is not available to anybody. It's embedded there inside by the manufacturer. Corresponding to the private key, there is a public key which is given to you, who you as the owner of this machine. Now, after that, and which is a public key, so actually you can give it to anybody else as well. So it is the and this public private key is of course certified by the certificate authority of this manufacturer. After that, there is we're saying that this TPM is capable of doing the crypto operations using this public private key pair, and it has some secure storage as well in the form of registers and maybe some memory, which is not accessible to anybody else. So any software or even some other hardware, which is not trusted hardware on your machine, so that's not accessible to anybody. Okay, and then your TPM supports an API. So it supports an interface basically, which is accessible through the device drivers, which talk to the your TPM. And this API is called the TPM underscore extend API. And this air API we are going to use next now to generate a proof of the software stack. And this API extends the content of the register with a supplied value. So we are going to assume for simplicity that there is only one register on TPM, and that one register we are saying here the PCR register. And when you give some when you call TPM, you're going to call this with TPM extend, you're going to call with some value, say X, and then it is going to extend the content of PCR register with this supplied value X. So now we are going to look at this API in the next slides. But before that, let me stop and see if there are any questions. So I hope that this is clear. We are talking about TPM, and these are some details about TPM. So it's the hardware. Okay. Now, regarding the TPM extend, okay, the TPM extend is your API. It takes as input a value v, which is typically a hash function, sorry, hash value, and it has a PCR register number. So here we are assuming there is only one register, and so you are going to give it only one value v. Okay, and so you are going to say call this API TPM extend with some value v. Okay, now what is the functionality of this API? The function basically corresponding to this API. So the functionality is that it is going to take the current value of the PCR register. So there is this register inside your TPM. Okay, so it is this going to take this register value. So register is also like a hardware component, right? So it is going to take this register value, it is going to concatenate it with v, and then it is going to take a hash over this entire value. And that the value that is generated, it is then going to store it in the PCR register. So your PCR register, let's say initially had value say 0, then it is going to take value 0, concatenate it with V, take the hash of this entire 0 extended with V, let's say SHA-256 hash of this value. And then the new value, which is the SHA-256 of this value, is going to be stored in the register. So this is our API, and if the value currently in the PCR is U, then after the TPM extend, the value in the PCR, the platform configuration register, becomes SHA-256 of the original value concatenated with the argument v, and this will be the new content of PCR. So the original content of PCR was u, and when you call this API TPM underscore extend of v, then the new value of PCR becomes SHA-256 of u concatenated with v. So now let me ask you some question. Let's say the initial value of PCR is equal to 0. Then you say TPM extend is going to call and with value 250, and afterwards TPM extend is called with say value 80. Then what will be the value of PCR after this? Did you understand what I told so far? Were you able to follow? So this is your TPM extend API, and this is the functionality. And this, if the initial value is u, and if you if the initial value of the PCR is u, if you call TPM extend once, then the value of PCR will become SHA-256 u concatenated with phi. Now, what will happen if you call TPM extend against with some value? Then how will the content of PCR change? That's the question. So is the SHA-256 of 250, which we get by doing the TPM extend first. So we say, so we are not, yeah, that is. And after that, here you've done add. Okay, does it mean extend? Extend would, so maybe you're using the concatenate. For concatenation, you are using here this value is concatenated. The original value is concatenated with 80, and then you are going to compute the SHA-256 over that, and then you store it in PCR. So yeah, so that is right. So that is what your TPM extend, this series of operation is going to do. That's absolutely right. And so then I think you have understood. And to make it more clear, we also have an example here. Suppose the value of PCR to start with is 0, then what is its value after invoking TPM extend with these three arguments, x, y, and z? So in the first step, the value of PCR will be this is 0. It will be extended with x. We will compute a SHA-256, and this will be stored in PCR. Next, for next value, for next TPM extend call, your original value is now what is there in the step 1. This is now your original value, SHA-256 of 0 extended with x. Then your input is y. So you're going to take this value, concatenate it with y, and then you're going to compute SHA-256 over that. And that is your value in PCR after step 2. Step third is, of course, you're passing z. So you're going to take the value from step 2, concatenate it with z, compute the SHA-256, and then you store this in PCR. So these are the steps. And so as you can see that this is a nested structure. So this is like a, initially this was the, this is your SHA-256, like this is a hash. This hash was computed over 0 extended with x. Then you compute the hash over the previous hash concatenated with some value. Then you compute the hash over the previous hash so far concatenated with z. So if you see that this is like a hash chain. So basically this is called a hash chain because you have some hash value, you concatenate it with your new value, compute the hash over it, you store it, then your new value is going to come, you're going to concatenate it again, then you're going to take a hash again, and then you store it again. So this type of computation, this kind of structure is called a hash chain. And uh, similar kind of a hash chain is also what goes in the blockchain. So if you've heard about blockchain, or if you have taken a course in blockchain, then you would know that in the blockchain, in the blocks, the head of the block contains this hash of the blockchain, like hash of the blocks before this block, which is the previous hash chain. Like in the step 3, let's say you are trying to add a new block in the blockchain, which is, let's say, now the step 3. So it is going to take the hash of all the blocks so far in the blockchain, which is stored in the previous block. So this is this value, and it is going to compute the hash of this new block, concatenate it with this, and then take a SHA-256 over that, and then store it there. So this indeed forms the basis of blockchain as well, that is the hash chains. And your TPM is also going to compute a hash chain. So if you're going to give it value x, it takes it, concatenate and do something. Then you give it value 1. Why? It going to take that, concatenate it with the previous hash value, compute a new hash value. So every time you call the TPM extend, it's actually extending the value. It's actually extending the content of the PCR register by computing by concatenating it with the previous value and then calling the SHA-256. So note that XYZ here are some like XYZ, some themselves. Like in for the example purpose, here we can give any value like 250, 80. But these in your system, when you usually pass this value to TPM, they're usually themselves like hash values. Okay. Now what are these hash value will become next clear soon. But let's say X is the SHA of some value V1, Y is the SHA of some value V2, and Z is the SHA of value V3. Then if you pass these values to your TPM in these 3 steps, then this will be your hash chain. So, and the security is provided by the guarantee of the SHA-256 function. The SHA-256 function cannot be reversed easily. So if you know the hash value, so you cannot basically, you will not be able to reverse it. You will not be able to find out that what were the original values which were used to compute the SHA-256. Okay, so so that provides the security guarantee, and the security guarantee here is provided by the hash function property that a hash function cannot be reversed easily. So it's a cryptographic hash function, okay, SHA-256. Now it's not necessary then the TPM that you have on your hardware is also using SHA-256. It may be using some other hash function and such as say SHA-512 or something. So it is just only for example purpose that we have shown that let's say the TPM extend does the hash 250, so SHA-256 computation. So we will just, I think it's already around 1. So I will stop in the 5 minutes or so. But given all of this information, how does attestation work? So now you have the server, which is your cloud provider server, which is AKA the prover, and your client, AKA the verifier, which is you. And you're going to challenge the server that prove to me what the software stack on your machine, and it is going to generate a response. So server must run a software stack which is amenable for attestation. What does that mean? Amenable for attestation, it means that the software stack would be modified in a way so as to assist in the attestation protocol. And why would the server then run such a software stack which is modified for attestation protocol? Because the server wants the business, right? It wants to prove to you, to the client, that I'm actually running the software stack that you're expecting. So the software, so what it means to say here that to assist in attestation, we have to change the software stack as well. Like it is not just a Linux OS which is running. The Linux will be running with some slight changes, okay, so that you can attest that the correct Linux is running. So there'll be some software changes, but we are not going to discuss those software changes today. We uh, like maybe tomorrow when I'm talking about control flow attestation, it will become a bit clear to you. But that is okay. We will look at one particular type of attestation here, and that is called in like today. I mean, in this particular, in these notes, we are looking at a particular type of attestation, and this attestation where we are verifying the software stack integrity, we are generating a proof of the software stack integrity. This is actually called trusted boot or secure boot, and this forms the basis for the other attestation protocols. Okay, so it's very important to understand this attestation, and because this will form the basis of other attestation protocols. So this particular attestation is called trusted boot or the secure boot, and this attestation protocol starts at the boot time. At the boot time, the server gives a snapshot of its software stack to the client, and then the software, and then who can verify it. So I will stop here, and then when I come back, when we will come back after the lunch break, then we will start looking from here. We will look at how can we use the TPM that we have discussed so far to generate a proof of the software stack. And this type of attestation is called secure boot. So we're going to discuss secure boot. So let's meet around 2:15, and then we will start. If you have any question, then please uh, put your question in the chat box and I can take them now. No, the TPM is not under the control of the client. The TPM is the hardware. It's actually not under the control of any entity. So think of it like my machine, my laptop, okay? And so you think of me as the remote server and you are the client. So you are going to give me your program to run, let's say, but before you do so, you want me as the server to give you a proof of the softwares that I'm running. Like, say, I am saying, okay, I'm running Ubuntu 20. Then after I am running, say, uh, Chrome, and I'm running my Teams, and these are the softwares that I'm running. Now, I need to generate a proof that you can verify that I'm actually running only these softwares and not any malicious software. Okay, so that's the problem setting. Now, to enable me, the prover, to generate a proof, uh, I need the trusted hardware, which is also trusted by you. Okay, so you, which is the verifier here, trust some component on my laptop, which is the trusted hardware. In this case, the TPM, the trusted platform module on my machine, you trust it. Now, why do you trust it? You trust it because you know that the TPM is secure by design. By design, nobody can tamper with the TPM. And you know that the TPM has a key inside it, which is embedded by the manufacturer. So let's say if my laptop is manufactured by Intel, so Intel has embedded a key inside the TPM. Now you do not actually trust me. You are only trusting that hardware which is there on my machine, and you do not trust any OS or any other software. And this hardware is actually not in the control of anyone. It's although it's on my machine, it's not even in the control of me. Even the owner does not have control over the hardware. So in the setting that we are talking about in the slides, so this hardware, although is present on the remote machine, which is controlled by a cloud provider, it's actually cannot even be controlled by the cloud provider. So the machine which the cloud provider is running has this TPM, which is not under the control of the cloud provider. And you as a client, you do not have control over this hardware. You only can, if this hardware generates a proof, basically a digital signature, then the cloud provider can give you this digital signature, and then you can verify that this signature was actually generated by the hardware. Okay, so you do not have access to this hardware remotely as such, and you do not control this hardware. Does that answer the question? Do you have any other question, follow-up question? Okay, thank you very much for the question. And please let me know if there are any doubts regarding so far regarding trusted computing. What is trusted computing? What is the problem setting? I hope it's clear what is trusted computing, what is the problem setting we are looking at right now. And then we talked about trusted hardware TPM. And after that, we are now going to look at how we can leverage this trusted hardware TPM to build a attestation protocol. In particular, we are looking at secure boot or trusted boot. If there is any question, please let me know. Otherwise, please feel free to go have your lunch, and then we will meet around at 2:15 and continue with trusted boot attestation protocol.